Next is about concept of DO, BOD and COD. Dissolved oxygen, biochemical oxygen demand and chemical oxygen demand. So dissolved oxygen refers to the amount of oxygen that is present in water and available for aquatic organisms to respire. It is a critical parameter in water quality assessment and is essential for the survival and growth of aquatic life. So DO levels are influenced by various factors including temperature, pressure and the presence of oxygen consuming substances. Key concepts in dissolved oxygen. Source of DO. DO in natural water bodies primarily comes from two sources like atmospheric dissolution. Oxygen from the atmosphere can dissolve into water at the water-air interface. Then photosynthesis. Aquatic plants and algae produce oxygen through photosynthesis, contributing to DO levels during daylight cycle. Then consumption of DO. DO is consumed by aquatic organisms through respiration. Fish, bacteria and other aquatic life depend on DO for their metabolic processes. Then DO saturation. DO levels are often expressed as the percentage of DO saturation, which indicates how much oxygen is present relative to the maximum amount that can be dissolved at a given temperature and pressure. Higher temperatures and lower pressure reduce DO saturation levels. Then significance and implications of DO. Aquatic health. Adequate DO levels are essential for the health and survival of aquatic organisms. Low DO can lead to fish kills and other adverse effects on aquatic ecosystems. Then water quality assessment. Monitoring DO is a crucial aspect of assessing water quality in natural and industrial environments. Low DO levels can indicate pollution or oxygen demanding substances in water. The eutrophication. Elevated nutrient levels in water bodies can lead to excessive plant and algal growth. When these organisms die and decompose, they consume DO, leading to hypoxia, low oxygen or anoxia, absence of oxygen, which can harm aquatic life. Then biochemical oxygen demand or BOD. Biochemical oxygen demand is a measure of the amount of oxygen consumed by microorganisms while decomposing organic matter in water over a specific period, usually 5 days. BOD 5. It is a key parameter for assessing organic pollution and water quality. And key concepts in BOD. Organic pollution. High BOD levels in water indicate the presence of organic pollutants such as sewage, agricultural runoff, or industrial wastewater. These substances provide a food source for bacteria, leading to increased microbial activity and oxygen consumption. Then BOD test. The BOD test involves incubating a water sample in a controlled environment for a specified period, commonly 5 days, and measuring the decrease in DO during that time. The difference in DO levels before and after incubation presents the BOD5. BOD5 by COD ratio. The BOD5 COD ratio is often used to assess the biodegradability of organic matter in water. A high ratio indicates that the organic matter can be readily decomposed by microorganisms. And significance and implications of BOD, wastewater treatment. BOD is a crucial parameter in assessing the effectiveness of wastewater treatment plants. It helps determine the extent to which organic pollutants are removed before the treated water is discharged into natural water bodies. Then water quality standards. Regulatory agencies often use BOD as a parameter to establish water quality standards and discharge limits for industrial and municipal effluents. Chemical oxygen demand. Chemical oxygen demand or COD. Chemical oxygen demand or COD is a measure of the amount of oxygen required to chemically oxidize and break down organic and inorganic substances in water. Unlike BOD, which relies on microbial activity, COD is a chemical test that provides a rapid assessment of water quality. So, COD is a measure of the amount of oxygen required to chemically oxidize and break down organic and inorganic substances. Okay. Then key concepts in COD. Chemical oxidation. COD involves the use of a strong chemical oxidizing agent, usually potassium dichromate K2CR2O7, to react with organic and inorganic compounds in a water sample. The reaction consumes oxygen. Then rapid analysis. We will be performing rapid analysis. So COD tests provide results more quickly than BOD results, making them suitable for assessing water quality in real time or for regulatory compliance monitoring. Significance and implications of COD, industrial effluent. COD testing is commonly used to monitor industrial wastewater discharges, ensuring that pollutants are within acceptable limits before releasing into natural water bodies. And water quality assessment. COD is an important parameter in overall water quality assessment, helping to identify the presence of organic and inorganic substances that may impact aquatic ecosystems. In conclusion, dissolved oxygen, biochemical oxygen demand, and chemical oxygen demand are critical parameters in water quality assessment and environment monitoring. They provide insights into the oxygen levels and organic pollution in water bodies, helping to protect aquatic ecosystems and ensure safe water for various uses. And sedimentation, coagulation, flocculation, filtration, etc. Sedimentation. Sedimentation is the physical water treatment process that involves the settling or removal of suspended solid particles from water or fresh wastewater. It relies on the principle of gravity to allow solid particles to settle at the bottom of a settling basin or tank, separating them from the liquid phase. And key concepts in sedimentation. Clarification. Sedimentation is primarily used for clarification, where the aim is to remove larger solid particles and turbidity from water. These particles can include sand, silt, clay, and organic matter. Then settling basins. Sedimentation basins or tanks are designed to slow down the flow of water, allowing sufficient time for particles to settle. The settled solids, often referred to as sludge or sediment, are then removed from the bottom of the basin. Then efficiency. Sedimentation efficiency depends on factors such as the size and density of solid particles, the depth and design of the settling tank, and the flow rate of water through the tank. Then applications and implications of sedimentation. Water treatment. Sedimentation is an essential process in water treatment plants to remove suspended solids before subsequent treatment steps such as coagulation, flocculation, and filtration. Then wastewater treatment. In wastewater treatment, sedimentation is used to separate solids from wastewater before further treatment or disposal. Then reservoir management. Sedimentation in natural reservoirs and lakes can impact water storage capacity, aquatic ecosystems, and sediment-related environmental issues. Then coagulation. Coagulation is a chemical water treatment process that involves the addition of coagulants to destabilize and clump together fine suspended particles into larger, more easily fittable aggregates called flocks. The coagulants neutralize the electrical charges on particles, promoting their collision and aggregation. Then key concepts in coagulation. Coagulants. Common coagulants include aluminum sulfate, alum, ferric chloride, and polyaluminum chloride. These chemicals work by creating positively charged ions in water, attracting negatively charged particles. And charge neutralization. Charge neutralization. Particles in water often carry negative charges due to the presence of ions or organic matter. Coagulants neutralize these charges, reducing electrostatic repulsion between particles. Then formation of flocks. As particles come into contact with the coagulant ions, they form flocks through chemical interactions and physical collisions. These flocks are larger and heavier than individual particles. And applications and implications of coagulation. Water treatment. Coagulation is a vital step in the removal of colloidal and fine suspended particles, organic matter, and color from water. It improves the efficiency of downstream processes like sedimentation and filtration. Then wastewater treatment. Coagulation is used in wastewater treatment plants to enhance the removal of pollutants including solids, phosphorus, and heavy metals. Then flocculation. Flocculation is a water treatment process that follows coagulation. It involves gentle mixing or aggregation to promote the growth and formation of larger, more stable flocks from the smaller aggregates created during coagulation. Then key concepts in flocculation. Mechanical mixing. Flocculation typically uses mechanical mixtures, paddles, or gentle agitation to encourage collisions between floc particles, allowing them to bond and grow. Then optimal floc size. The goal of flocculation is to achieve the formation of flocks for the optimal size, which is large enough to settle efficiently in subsequent sedimentation process. Application and implications of flocculation. Water treatment. Flocculation is a critical step in water treatment, ensuring that flocks formed during coagulation are of right size and stability for effective removal in sedimentation tanks. And wastewater treatment. Wastewater treatment and flocculation helps improve the settling characteristics of flocks, leading to more efficient removal of pollutants. And filtration. Filtration is a physical water treatment process that involves passing water through a porous medium or water bed to remove suspended particles, flocks, and other impurities. And key concepts in filtration. Filter media. Common filter media include sand, anthracite coal, diatomaceous earth, and multimedia filters that use layers of different media. These media have varying sizes and densities to trap particles. Then filter types. Filtration can be accomplished using rapid gravity filters, slow sand filters, or pressure filters depending on the application and desired treatment level. And applications and implications of filtration. Water treatment. Filtration is the final step in water treatment, providing a physical barrier to remove remaining particulate matter and microbes, resulting in clear and safe drinking water. And wastewater treatment. Filtration is used in tertiary treatment process for wastewater to remove suspended solids and further reduce the concentration of contaminants before discharge or reuse. In conclusion, sedimentation, coagulation, flocculation, and filtration are integral processes in water and wastewater treatment, collectively ensuring the removal of suspended solids, turbidity, and other impurities to produce clean and safe water for various purposes while protecting environmental health. And pH and redox potential. pH, acidity and alkalinity, key concepts. pH is a measure of the acidity or alkalinity of a solution. It quantifies the concentration of hydrogen ions H plus in the solution. The pH scale ranges from 0, very acidic, to 14, highly alkaline or basic, with 7 representing neutrality. And hydrogen ion concentration. The pH scale is logarithmic, meaning each unit change represents a tenfold difference in hydrogen ion concentration. A decrease in pH by 1 unit corresponds to a tenfold increase in H plus concentration. And acidic solutions. Solutions with a pH less than 7 are acidic. They have a higher concentration of H plus ions. Examples of acidic substances include vinegar, pH, and lemon juice, pH 2 to 3. Alkaline or basic solutions. Solutions with a pH 7 are alkaline or basic. They have a lower concentration of H plus ions, may contain hydroxide ions or H minus. Examples include baking soda and household ammonia. So, significance and implications of pH. Biological systems. pH plays a crucial role in biological systems where it affects enzyme activity, cellular processes, and the health of organisms. Most organisms have a narrow pH range in which they can thrive. And water quality. pH is a critical parameter in assessing the quality of natural waters. It can impact aquatic life as many aquatic organisms are sensitive to pH changes. Then chemical reactions. pH influences chemical reactions in various fields, including industrial processes, agricultural and analytical chemistry. Then buffer systems. Buffers are substances that resist changes in pH. They are essential in maintaining pH stability in biological systems and some industrial processes. And redox potential or EH. Key concepts in redox potential. Redox potential, often denoted as EH, measures the tendency of a chemical system to undergo reduction, gain of electrons, or oxidation, loss of electrons. It quantifies the electron activity in a solution or system. Electron donors and acceptors. Redox reactions involve the transfer of electrons. Redox reaction involve the transfer of electrons from electron donors, reducing agents, to electron acceptors, oxidizing agents. In EH measurements, a reference electrode, such as a standard hydrogen electrode, is used as a reference for electron activity. EH measurement scale. The EH scale can range from highly reducing negative values to highly oxidizing positive values. Negative EH values indicate a reducing environment, while positive values indicate an oxidizing environment. Then redox couples. Redox potential is often described in terms of redox couples such as Fe2+, Fe3+, or O2H2. These couples involve the interconversion of two species within different oxidation states. Then significance and implications of redox potential. Environmental redox conditions. EH measurements are crucial in understanding and characterizing redox condition in environmental systems, including soil, sediments, groundwater, and aquatic ecosystems. These conditions influence the mobility and transformation of pollutants and nutrients. And biogeochemical processes. Redox potential is central to biogeochemical process, including microbial respiration, iron and sulfur cycling, and the transformation of contaminants like heavy metals. Then water treatment. In water and freshwater wastewater treatment, EH measurements can be used to optimize treatment processes, especially those involving the removal of contaminants through redox reactions. Then corrosion control. Understanding EH is important in controlling corrosion of metals as it helps predict the conditions under which metals may oxidize or reduce, potentially leading to corrosion. Then electrochemical technologies. Redox potential is essential in electrochemical technologies including batteries, fuel cells, and electroplating process. Then bioremediation. In bioremediation, EH measurements guide the selection of appropriate microbial processes for the cleanup of contaminated sites. And in conclusion, pH and redox potential are crucial parameters in environmental science, chemistry, biology, and various industries. They provide insights into the chemical and electron activity of solutions and systems, influencing a wide range of processes and applications from water quality assessment to corrosion control and bioremediation. Then inorganic and organic components of soils. Inorganic components of soils. Mineral particles. Sand. Sand particles are the largest among soil particles with diameters ranging from 0.05 to 2.0 millimeters. Sandy soil have good drainage but poor water and nutrient retention. Then silt particles are smaller than sand but larger than clay with diameters between 0.02 and 0.05 millimeters. So silty soils have moderate water retention and fertility. Then clay. Clay particles are the smallest with diameters less than 0.02 millimeters. Clay soils retain water and nutrients exceptionally well but can have poor drainage. Then silt and clay fractions. Colloids. Silt and clay particles are colloids which have high surface area and can attract and hold ions. This property is crucial for nutrient retention and cation exchange capacity, or CEC. And soil pH, acidity and alkalinity. The pH of soil determines its acidity and alkalinity. Soils can range from acidic, neutral to alkaline. pH influences nutrient availability and microbial activity. And cations and anions. Cation exchange capacity. CEC is a measure of the soil's ability to hold and exchange positively charged ions or cations like calcium Ca2+, magnesium Mg2+, and potassium K+. And anions. Soils also hold negatively charged ions or anions like nitrate NO3- and sulfate SO4(2-). Organic components of soils. Organic matter OM. Humus. Humus is the decayed organic matter in soils. Rich in stable organic compounds, it improves soil temperature, water retention, and nutrient availability. Then plant residues. Decomposed plant materials such as leaves, roots, and crop residues contribute to soil organic matter. Plant residues. Decomposed plant materials such as leaves, roots, and crop residues contribute to soil organic matter. Then microbial life. Microorganisms, bacteria, fungi, algae, and other microorganisms are essential components of soil. They decompose organic matter, release nutrients, and contribute to nutrient cycling. And microbial biomass. The living component of soil organic matter include microbial biomass, which plays a vital role in nutrient transformations. And microorganisms, earthworms. Earthworms are soil-dwelling organisms that improve soil structure by burrowing and mixing organic matter with mineral particles. And arthropods. Insects and other arthropods contribute to the breakdown of organic matter and nutrient cycling. Then roots. Plant roots. Plant roots add organic matter to the soil as they grow and die. They also help stabilize the soil structure and improve water infiltration. Then significance and implications. Nutrient cycling. Organic matter and soil organisms play a vital role in nutrient cycling, making essential nutrients available to plants and regulating their availability. And soil fertility. Organic matter improves soil fertility by enhancing nutrient retention and release. It also serves as a source of nutrients for plant growth. Then soil structure. Organic matter improves soil structure, preventing compaction, promoting aeration, and enhancing water holding capacity. Then water retention. Organic matter helps soil retain moisture, reducing water runoff and erosion while providing a buffer against drought. And microbial activity. Soil microorganisms are key drivers of decomposition and mineralization process, influencing soil health and productivity. Then sustainability. Understanding the balance between inorganic and organic components is critical for sustainable agriculture and land management practice. And in conclusion, soils consist of both inorganic and organic components, each playing a vital role in soil fertility, structure, and overall health. A thorough understanding of these components is essential for sustainable land use, agriculture, and environmental management. The next, biogeochemical cycles: nitrogen, carbon, phosphorus, and sulfur cycles. So we'll be shortly discussing all this, not in detail explanation, just a surface level explanation. Okay, first, nitrogen cycle. The nitrogen cycle describes the movement. First, nitrogen cycle. The nitrogen cycle describes the movement and transformation of nitrogen through various reservoirs in the Earth ecosystem, including the atmosphere, soil, and living organisms. Key processes in the nitrogen cycle include nitrogen fixation. Nitrogen gas in the atmosphere is converted into ammonia or ammonium ions by nitrogen fixing bacteria. This can occur in the roots of legume plants or in free living soil bacteria. Then nitrification. Ammonia or ammonium ions are converted into nitrite and then into nitrate, NO2 minus and NO3 minus, by nitrifying bacteria. This process makes nitrogen compounds available to plants. Then assimilation. Plants take up nitrates and ammonia from the soil and incorporate them into proteins and other organic compounds. Then denitrification. Denitrifying bacteria convert nitrates and nitrites back into nitrogen gas, releasing it into the atmosphere. Then ammonification. Decomposers break down organic matter from dead organisms and waste materials, converting nitrogen containing compounds into ammonia. Then significance and implications of the nitrogen cycle. Nitrogen is an essential component of amino acid, proteins, and nucleic acids, making it vital for all living organisms. Human activities such as the use of synthetic fertilizers and industrial emissions have significantly altered the nitrogen cycle, leading to environmental issues like eutrophication and nitrous oxide emissions, a potent greenhouse gas. And carbon cycle. The carbon cycle describes the movement of carbon through the atmosphere, terrestrial ecosystems, oceans, and living organisms. Key processes in the carbon cycle. Photosynthesis. Plants and some microorganisms absorb carbon dioxide from the atmosphere and convert it into organic compounds, primarily glucose, through photosynthesis. Then respiration. All living organisms release CO2 into the atmosphere as a byproduct of cellular respiration. Then decomposition. Decomposers break down dead organic matter, returning carbon to the soil as organic carbon or releasing it as a CO2 through microbial respiration. Then combustion. The burning of fossil fuels such as coal, oil, and natural gas releases CO2 into the atmosphere. Then deforestation and wildfires also contribute to carbon emissions. Then carbon sequestration. Some carbon is stored long term in forests, soils, and the ocean. This process helps mitigate the greenhouse effect by reducing atmospheric CO2. And significance and implications of the carbon cycle. The carbon cycle regulates Earth's climate by influencing the concentration of greenhouse gases like CO2 in the atmosphere. And human activities, especially the burning of fossil fuels and deforestation, have led to an increase in atmospheric CO2 levels, contributing to global warming and climate change. Then phosphorus cycle. The phosphorus cycle describes the movement of phosphorus through the earth crust, soil, water, and living organisms. Key processes in the phosphorus cycle. Weathering. Phosphate rocks in the earth crust release phosphate ions, PO4 3- through weathering process. Then uptake. Plants absorb phosphate ions from the soil and animals obtain phosphorus by consuming plants or other animals. Then there will be decomposition. Phosphorus is released from dead and organic matter through decomposition and returned to the soil. Then sedimentation. Phosphorus can become sediment in aquatic ecosystems, eventually forming sedimentary rocks. Significance and implications of the phosphorus cycle. Phosphorus is a crucial component of DNA, RNA, and ATP, playing a vital role in energy transfer and genetic information. Phosphorus is a crucial component of DNA, RNA, and ATP, playing a vital role in energy transfer and genetic information. An excess of phosphorus runoff into aquatic ecosystems can lead to water pollution, eutrophication, and harmful algal blooms. Next, sulfur cycle. The sulfur cycle describes the movement of sulfur through the atmosphere, terrestrial ecosystems, oceans, and living organisms. Key processes in the sulfur cycle. Weathering. Sulfur containing minerals in rocks release sulfate ions, SO4 2 minus through weathering. Then biological sulfur cycle. Sulfur is cycled through the environment by sulfate reducing bacteria which convert sulfate into hydrogen sulfide and sulfur oxidizing bacteria which convert H2S back into sulfate. And volcanic emissions. Volcanic eruptions release sulfur dioxide SO2 and hydrogen sulfide H2S into the atmosphere. Then human activities. The burning of fossil fuels and industrial processes release sulfur dioxide SO2 minus into the atmosphere. Then significance and implications of the sulfur cycle. Sulfur is a key component of amino acids and vitamins in living organisms. Sulfur dioxide emissions can lead to air pollution and the formation of acid rain, which has detrimental effects on ecosystems, soil, and infrastructure. In conclusion, biochemical cycles, including nitrogen, carbon, phosphorus, and sulfur cycles, are critical processes that regulate the flow of essential elements to the Earth's ecosystem. So, understanding these cycles is crucial for environmental science and management as they impact climate, nutrient availability, and ecosystem health. And toxic chemicals, pesticides, and their classification and effects. Let's provide a comprehensive explanation of this topic. Pesticides. Pesticides are chemical substances or mixtures used to control, repel, or kill pests that can damage crops, harm livestock, or pose health threats to humans. Pests include insects, weeds, fungi, rodents, and other organisms. Pesticides play a vital role in modern agriculture, forestry, public health, and vector control. In classification of pesticides. Pesticides are classified into several categories based on their intended use, chemical composition, and mode of action. Insecticides, designated into control insects. These are among the most widely used pesticides. Examples include organophosphates, pyrethroids, neonicotinoids, and carbamates. Herbicides, used to manage and kill unwanted plants or weeds in agricultural fields, gardens, and lawns. Common herbicides include glyphosate, atrazine, and 2,4-D. 2,4 fungicides. 2,4-D. That's it. These are some herbicides, which are the glyphosate, atrazine, and 2,4-D. Then fungicides are there. It is designed to combat fungal diseases that affect crops and plants. They include chemicals like copper-based compounds and azoxystrobin. Then rodenticides, developed to control rodent populations that can damage crops and transmit diseases. Rodenticides may include anticoagulant chemicals such as warfarin and bromadiolone. Then nematicides target nematodes, microscopic worms that can damage plant roots. Chemicals like aldicarb and phenamiphos are examples. Then molluscicides, used to control snails and slugs which can damage crops and transmit diseases. Methaldehyde is a common molluscicide. Then acaricides, designated to combat mites and ticks that infect crops and animals. Examples include abamectin, and fenpyroxenate. And effects of pesticides. While pesticides offer numerous benefits, including increased agricultural productivity and reduced disease transmission, they also raise environmental and health concerns due to their potential negative effects. Environmental effects, non-target species. So, environmental effects, non-target species. Pesticides can harm beneficial insects, birds, and aquatic life when they are unintentionally exposed. Then residue accumulation. Pesticides residues can accumulate in soil, water, and food chains, impacting ecosystem and food safety. Then pesticide runoff. Rainwater can wash pesticides from treated fields into water bodies, leading to water pollution. Then pesticide resistance. Overuse will lead to pesticide resistance of pest populations, making control more challenging. Then human health effects will be there. Acute poisoning. Accidental exposure to high pesticide doses can cause acute poisoning in humans, which might lead to death. So, leading to symptoms ranging from nausea to more severe effects, including death. Then chronic health effects. Long-term exposure to low levels of pesticides has been associated with various health problems, including cancer, neurological disorders, reproductive issues, and developmental disorders. Then occupational risks. Farm workers and pesticide applicators are at risk of pesticide exposure, and proper safety measures are essential to minimize these risks. Then residues in food. Pesticide residues can persist on fruits, vegetables, and grains, potentially exposing consumers to low levels of pesticides to their diet. Then economic and social effects. Cost-benefit trade-off. The economic benefits of pesticide use must be weighed against the costs of environmental damage and health impacts. And food security. Pesticides contribute to global food security by protecting crops from pests, helping ensure an adequate food supply. Then regulation and safety measures. Regulatory oversight. Pesticides are subject to strict regulation in most countries, with agencies such as the Environmental Protection Agency in the United States and the European Food Safety Authority in Europe overseeing their approval and use. Then integrated pest management (IPM). IPM strategies aim to minimize pesticide use by integrating multiple approaches, including biological controls, crop rotation, and selective pesticide use. And pesticide labels. Pesticides came with detailed labels specifying their safe use, application rates, protective measures, and environmental precautions. Thank you for listening.